All right, so we just ran a simulation using the simulation function I created to compute the difference between decisions about female hiring or promotion and decisions about male promotion. So when we run it, note that you have this long output with tons and tons of numbers, 1,000, and that's, a good, very large number that allows us to say what's likely, what's not likely, right? Now, when you're knitting the document, you can only imagine that printing 1,000 numbers will take a lot of space. So when you have long outputs like this, just comment it out before knitting, okay? All right, so now that we ran the simulation, we saved everything inside that little container. We can, so after repeating the experiment multiple times, we have multiple estimates of the sample statistics of interest. Here, the difference in male and female promotion votes under complete chance conditions. You saw it. There was nobody making these decisions, so it was completely randomized. Because we have a bunch of sample estimates of proportion differences, we can now create a sampling distribution and assess what are typical and atypical values. First, let's put the variable promotion diff, which has the data from the 1,000 experiments, inside a data frame. All right, so because ggplot is a function that takes as the first input, if you can remember, the data frame, not a vector. So we're going to put the promotion diff vector that has the 1,000 replications of the results of the 1,000 replications of the experiment inside an object called class simulation. And we're going to transform that into a data frame by saying data frame class simulation, because as of now it's just a vector. And now we're going to put a name to that vector called promotion diff. So if we do that, now we have the class simulation here, and we have the 1,000 values of difference. Now, if we come here and we look at the range of values that we can expect by chance alone, we can say, hey, get me the range R of the variable promotion difference that is inside the newly created class simulation dataset. So you can see here that differences between decisions for male and female promotion can be as large as 45%, 46% in both directions, right? It can happen just by chance. Remember, here we're assuming chance because there is nobody making these decisions, and we can see that under fully random conditions, we can get things as large as 45. That's why when you get a sample difference, you can't assume from the get-go that this is, oh, this can't happen. Well, it can. The question really is, with what likelihood? If the likelihood of a 30% difference or more is high, then we need to be careful, because it can happen by chance with a high frequency, high likelihood, so it's plausible. We can't claim gender bias with any confidence, right? So that's why we do this. Now let's plot the full distribution. So ggplot is taking class simulation as the data set it needs to look at. It's putting promotion difference on the x-axis, and then it's plotting from negative 0.6. We actually don't need negative 0.6 in this particular simulation, so we can go from negative 0.5 to 0.5. If you don't want to change, that's fine. It just can't be less than the extremes in the data. And we're coloring, we're putting our little titles as you've learned from before. So now let's look at the histogram. Oh, look at this. So here's 30% is about here, right? So you can see that 30%, negative 30% difference or more is Very, very few compared to differences right around 0. It's random. That's what we would expect, right? That these bars would be higher because, you know, it's random. It should be about the same in the two piles. But we see a distribution that looks a lot like the normal distribution, right? So we can compute what's the probability of getting negative 30 or less, 30 or more, just 30, you know. Now let's think about this in the next steps. Making a decision based on data from a random experiment. What should be considered rare? In statistics, we assess how typical or plausible or rare, not so plausible, an event is based on probability. The questions scientists try to answer with statistics take the following more precise form. With what probability can I expect my observed sample statistic to show up in a distribution, describing the data obtained from repeated instances of a random experiment, right? With what probability can I expect my result to happen? My result or more extreme to happen. Two possibilities. If the probability is high, and high in the field of statistics is something that's more than 5%. Oh, but 5% is so low. Yeah, but that's the idea of you're innocent until proven guilty beyond reasonable doubt. So we want to be conservative here. Anything above 5%, we say, it's kind of plausible, the probability is high, so you don't reject the null. That's where the 0.05 comes from. It's the likelihood of observing your data under random conditions, right? If the probability is low, typically less than 0.05, scientists reject the null and assume that there is gender discrimination going on, all right? Because the precise 30% value might not be in the distribution, we compute the probability of finding a 30% difference or larger. Now you can ask, how exactly do we compute the probability of our observed data under the null hypothesis? And that will depend on the nature of the alternative hypothesis. Possibility 1. Let's assume first that we had no idea from the beginning, there was no theory, no observation from before that would suggest that gender might be, what gender might be discriminated against during promotions. We have no idea. We're beginning exploring this field and we don't know if discrimination is against males or females. In this case, we need to find the probability of observing a difference greater than 0.30% or 30%, or smaller than negative 30. This is the same of saying that we need to run what you probably heard in your undergraduate statistics, a two-tailed test, right? Because we're going to consider weird and extreme values that are above 30% or less than negative 30%. Because we don't know if we can expect extreme in both directions, in which direction we should be expecting that difference to lie. So we have our data on a data set called class simulation. So we're asking R to open it up, look inside of there and mutate that data set and create a new variable called greater than absolute 30, which means we're going to put true if you have promotion decision that's greater than 0.30, or, this is an OR operator, promotion differences that are less than negative 30. So we're trying to get both extremes. And then when we do that, let me just run this piece. You can run both at the same time, but I just want to show you what happens when I run this piece, is that I'm going to modify our class simulation data set, and now I have a greater than absolute 30 rule. And it's false when it's either less than 0.30 or it's false when it's greater than negative 0.30. So let's try and find a true here. It's going to be rare, but it's going to be there somewhere. Should we waste time with this? I don't know. Let me stop. It took me some time, but I found a true one. Look at that. It's greater than 0.30, so you see a true value right there. So we created this new, you should remember that's a, what kind of variable is this? logical variable because it can take a value of true or false, you are correct. Now, if you take the mean of a logical variable greater than absolute 30 is a logical variable, and that's inside class simulation. If you take the mean, R will give us the proportion, right, of observations that are either greater than 0.30 or smaller than -30. So let's run both of them, and we can see that the proportion of all of the observations where the difference was greater than 30 or smaller than -30 was 0.007. That is so much less than 5% than the 0.05, right? It's much, much less. It's very unlikely to see this. So if it is unlikely, we say there's gender bias because under random conditions, we don't see a difference of 0.30 or more or -0.30 or less very frequently, right? So, question 9. Which inferential statement is supported by the probability just computed? Read A and B and think about what your response would be. Stop the video and then come back when you're ready for the answer. So A says, the experiment on gender discrimination provides evidence that promotion decisions are affected by gender. I should say assigned sex because really that's what they measured. Because the probability of finding a difference in promotion rates of males and females at least as large as 30% in either direction is very low under random conditions, smaller than the typically accepted threshold of 5%. So this is correct. We cannot say that there is no evidence of that promotion decisions are biased by assigned sex because it's not very likely, right, to see a difference of 30%, absolute 30% or more. Now, possibility 2, which is what probably we would do in this situation, we're going to assume that we have reasons to believe that there is one possible kind of discrimination, which is against females. In this case, we need to find the probability of observing a difference greater than 0.30, and anything below that is evidence of no discrimination because there is really no reason to believe that you would have extreme values in the other direction. In the case of discrimination discrimination against gender-based discrimination or sex-based discrimination, because all evidence points to if there is any discrimination, it is against females, not males. All right. So let's compute then, and that would be the same as running what you probably heard in statistics, a one-tailed test. We're going to come back to these concepts when we run different tests, but I wanted you to understand when do we use one, when do we use the other, right? So let's compute then the probability of having a difference in promotion rates of 0.30 or larger. So we need to modify this code here. We need to create another variable that will have a true value, not for when data is greater than absolute 30, but data that is greater than, or I should say smaller than, -30, that would indicate discrimination against female because we computed the proportion by subtracting male from female proportion. All right, we'll do that when we come back. Try and modify the data set to create that variable. Right. So you need to use this to create the new variable here. Do the modifications that you believe is necessary, and we'll come back to check. Now I really believe that's going to be our last video. All right. See you soon.